So I'm going to try and keep this short because it's only a 12-minute talk. It should be smaller than this so that we can have a conversation. I'm not going to show any science results, although you will have seen some earlier today. Eric showed some results from the Einstein probe and the 240315A, the one that was at 4. Redshift 4. That counterpart was found in Atlas by my boss, bless him, who was consulting the GCNs. So we have science results, but today I'm going to walk you very quickly through the journey of the data as we get it. So Atlas is an optical sky survey. Does it work? No. The specs briefly are like this. We've got 4 telescopes, 4 units, 2 in Hawaii, 1 in South Africa, 1 in Chile, so we can observe the northern and the southern hemisphere. We observe the sky in a tile. We go back to the same spot every 24 to 48 hours, depending on which part of the sky it's in and if it is observable. And every night we observe the same patch of sky 4 times in 30-second exposures, separated by 15 minutes. Now, this is pretty standard strategy for finding near-Earth asteroids, but it's also very, very convenient if, like me, you're interested in extragalactic transients. So Atlas is funded for near-Earth asteroids, for solar system objects, but we are vultures, and we are very much using that data. So the magnitude limit in both of our filters is roughly 19.7. So if you're any lower than this, you're going to have to stack your images, your 30-second exposures. And if, unfortunately, you're interested in stars that are brighter than 12th magnitude, we completely mask them out because they are too bright. So what happens to the data once it is obtained? First, it is reduced on site at the telescopes. Then it is moved to Hawaii, where this is the difference imaging is actually processed. So if you're a neutrino physicist and you're not familiar with difference imaging, it's pretty simple. We've got our picture that we took tonight, and we've got a reference image. We take the difference, and if we have a transient and everything went well, which it doesn't always do that, your transient should glow brightly in the center of your image. And then all of this information is transferred then to Queen's University Belfast, where most of the processing happens. I've put a picture of Ken Smith, our server wizard, the man who makes all of this work together. If you've got a problem with Atlas data, he's the one you should consult. So once we have the difference images, the first thing that happens is quality cuts, because for 1 night worth of data from 4 telescopes, we get about 10 million alerts. That's on the low scale of what we get. Now, some of this is going to be known variable things, stars, active galactic nuclei, which you can cross-match with Sherlock. We'll talk more about this in just a second. Some of it is genuine garbage because difference imaging does not always go right. So we have some real bogus classification with some fancy machine learning happening. And then when you're done with this, we prioritize what's left of the data stream, and eventually we show it to the eyeballers. Yes, that is a technical term, the people that eyeball the data, and if it's good, send it to the TNS. So Sherlock, Dave Young is the man there. He's still the maintainer of Sherlock, and he's the one who came up with it. Essentially, it's a big cross-matching service for catalogs. Since he created Sherlock, a bunch of little copies have popped up, like Adler and Moriarty, all on the theme of Sherlock for different telescopes. And what it does is that it classifies your transient into different categories based on its location on the sky. So if it is located near a known variable source, it will give it that label. If it's located near a galaxy, it will either call it a nuclear transient or a supernova, depending on its location with respect to the center of that galaxy. And if it doesn't find anything, then it will be an orphan or unclear. It also gives us possible associations with gravitational wave alerts. So this is really useful because you can move the known variables away. You can keep them in the database, but you can remove them from your data stream. But the next thing you need to do is some real bogus classification. Now you might think, why didn't you do that before? And that's because that is a lot of computing. And if you have millions or even tens or hundreds of thousands of alerts, you don't want to do all of that compute. So you do it with what's left of the data stream. Now, our CNN is going to work on the difference image, specifically the center of the stamp, a 20 by 20 pixel cutout. And it's going to give it a score between 0 and 1, 0 being bad, 1 being good. Essentially, it's trying to see if the blob in the middle is PSF, like it's nice and round, because that's what optical astronomers are looking for. Now, in our current strategy, if it gets a score above 0.2, it is kept. If it's below 0.2, it is garbaged. Now, the important thing to know is when I say that something is garbaged in Atlas, I do not mean that it is deleted. It is not deleted, it is in the database, but it is labeled as garbage and the eyeballers no longer see it. So that's the way that things used to work until 23rd of August. So you've got your tens of millions of alerts, you've got your basic cuts, your Sherlock cuts, you bring it down to a few thousand, you do the RB score and the threshold, and you're left with hundreds of alerts in your eyeball list every single day. And you have to eyeball everything because the telescopes do not stop. The eyeball list fills up every day, a few times a day, actually. So I took a look at this, now that was known by the eyeballers, but my project was to make their life a little bit easier. And the problem with this eyeballing is that hundreds of images are fun to look at if it's real astrophysical transients and fun galaxies, but 85% of these things were genuine garbage. Things are not fun to look at and not useful. So there's a lot of automation that is left to do here. And so I made something called the Virtual Research Assistant. I'm not going to talk too much about it because it is my pet project, but I'm here to talk about Atlas. And what it does is essentially it curates the eyeball list. So instead of giving everything with a real burger score above a certain threshold, it will score your alerts and give it a rank. And the higher the rank, the more interesting it is for you. And then we have a policy: everything below a certain rank is garbage, everything above a certain rank is shown to the eyeballers. And when you do that, you go from hundreds of images a day that need eyeballing to between 5 and 50. Now, I did some statistics for last week, and I'm very happy with the numbers. I'm a little too happy with the numbers. Normally things, thank you very much, normally things don't work that well that quickly, so I am suspicious. But last week we had 3,000 alerts that made it to the eyeball list after the CNN cuts, after the real bogus classification cuts. With the VRA, 380 of those were actually shown to humans, and over 83% were garbaged automatically. Of the things that were shown to humans, which is everything that has an actual color, most of it was either real extragalactic. I'm sorry that good mean extragalactic transient. If you're galactic transient, you'll see my bias. But everything, most things were extragalactic or galactic transients, and we did have a little bit of garbage left. But what I find really encouraging with this plot is that 6% of the total data that was ingested was good and recovered. And in the training data, which is real Atlas data over the past four and a half months, something like this, 6% of that data is good. So I'm not ditching half of the good alerts with the VRA on accident. Seems to be working. But of course, once the data has been processed, you want to access it. That is the point. So where does the data end up? If it is good, and it is actually labeled as good by a human, not by the VRA, by a human, it will get sent to the TNS, the transient name server, and then you can have access to it. You can have access to all of the data through the force photometry server, whether it has been in the TNS or not. You just need an ARIAN deck and then you can get it. It's genuinely accessible tool. You can register very easily. You'll be given an account, and then you can do everything through the web. That's what's available now, and what is about to come is the Atlas API client. So in order to make the VRA, I had to make the Atlas API actually work, but it means that you can access programmatically all of the data in the database and get it in JSON format. So I'm not going to keep that to myself. I'm going to clean it up. I've got a research software engineer working with me so that we can actually unit test this thing and make sure that it is usable by other people. And hopefully around mid-November, you will have an Atlas API client so that you can request data for your favorite object. I think that's it for me. So yes, so thank you very much for listening. I really look forward to the Sciathon because it's not just about the data that you can get from Atlas, it's the data that you think might need to be in Atlas or in the VRA. If you have data that you think I should be listening to, please let me know, and I'd love to work with you in the Sciathon later this week.